All right, let's talk about limits, but not just from the pre-calculus and beginning calculus perspective, but the perspective of the praxis exam where you've had lots of calculus. There are what I call the regular limits. I'll show you what those look like. That's the default. You use your regular limits. That's your default approach. And then there's also the L'Hopital's limits. I don't know if I'm saying it exactly right either, but it's a French or Swiss name, so I kind of get the impression you don't pronounce all the last um, letters. Not sure. I'll just call it L'Hopital. That's the special kind. For a regular limit, you don't need any special rules. You just take it, right? Limit as x approaches, whatever. And I'm just going to say, I'm just going to write a scribble in here. X approaches a, that's some constant. And then, whatever it is. It could be exponential, it could be a fraction, could be a polynomial, right? Could be all kinds of things. Sometimes, right? Sometimes you get a number, right? Sometimes you get an answer, right? So if you get a number, then that's your answer. Right, like if it was a fraction, 3/7, you get 3/7. If it's 3 to the 7th power, you reach for your calculator, or you hope that your multiple choice is written in exponential form. So number means no problem. Now, of course, sometimes you do have messes, and one special kind of mess is when it's a fraction. Oh, let me back up just a moment, right? Sometimes you have limits involving infinity, right? Sometimes you have limits where you're supposed to let x approach either negative or positive infinity, right? You kind of have to imagine large numbers, right? You're not actually going to get a specific number out because you're imagining what happens when I get larger and larger in the positive direction, or, larger and larger in the negative direction. Generally, what you're going to get there is you're just going to get infinity, right? The quantity just keeps getting larger and larger, maybe in the negative direction. But one other interesting possibility is that the top of your fraction, this has to involve a fraction, you've got a number divided by infinity. Or, maybe it's a constant number, maybe it's a little varying number, but it just varies and stays small. This answer, right? So when you have an answer of infinity, you say undefined limit. That's all, undefined. When you have a number divided by plus or minus infinity, when you think about those infinite limits, you say 0. The limit is actually the number 0. Shrinking closer and closer and closer and closer to 0 as a limit means the limit is equal to 0. It's an interesting distinction, right? You're checking by looking at what happens as a pattern, but if the pattern shrinks to nothing, you say nothing, 0 is the answer. Again, a number is an answer. A non-number like infinity, plus or minus, is considered undefined. Or there is no limit, or the limit diverges. Language varies. This idea of a fraction is important because there is one other possibility. For the infinities, you could get infinity over infinity, right? That means both the top and the bottom are growing. And the question becomes, who's growing faster? Or are they growing at the same rate? Or is one of them growing like 1.5 times faster than the other? Are things stabilizing or not stabilizing? That's the question. You were taught a few methods for dealing with that with polynomials. you no longer need to use those methods because L'Hopital's rule is designed for the infinity over infinity scenarios. And again, plus minus, right? A plus or a minus sign doesn't really matter. And there's one other, right? When you have fractions, right? A fraction, remember when we had division by zero, right? Division by zero is that plus or minus infinity. Sorry, division by zero sometimes happens when you've got something like x minus a on the bottom and a number on the top. A number divided by zero, that's also undefined. That's a different kind of infinite answer. But sometimes a fraction can be 0 over 0. That also is what L'Hopital's rule is for. Now this is simplified L'Hopital's rule. You don't need to worry about it for the praxis, but there are other forms where L'Hopital, infinity to the power 0, 0 to the power infinity, other weird things where, you know, you can't quite figure out what rule is the most important, right? We were told any number to the power 0 is 1, but infinity is not a number. We're also told that 0 to the power infinity, well, 0 to any power is 0, but infinity is not a number, right? It's just a tendency. So there are other cases. That's advanced L'Hopital stuff. I just wanted to mention it for the purposes of the praxis calculus course. It's just going to be these two scenarios. Now, this is very important. Listen hard. You must have one of these two scenarios. You must have one of these two scenarios for L'Hopital to be legitimate. That's a requirement, right? You are not allowed to use the L'Hopital rules in any other situation. That's what tells you whether or not you can use L'Hopital's or you have to do your regular stuff, okay? Always default to the regular because you're going to do your regular computations. And, you know, if there's a fraction involved, right? If there's no fraction involved, you're going to get an answer or, you know, goes to infinity. If there is a fraction involved, there's a possibility you'll get one of these two funny looking fractions. Then L'Hopital's rule is required. Remember, it has to be funny looking. 0 over infinity, that's just 0, right? That's, sorry, that should be green ink. That's just 0, right? Infinity over 0, you know, that's just undefined, just like, you know, just like a large number divided by 0 is undefined. What else we got? 0 over infinity, infinity over 0. Yeah, those are the other cases, right? A number over 0, also undefined, right? And a number, well, any number, not just 0, any number over infinity turns into 0 as the answer because the infinity gets so large it cancels out whatever size that constant number is. Remember, as a limit. So you can still get undefined as an answer. You can still get fractions involving infinity and 0 and get answers. In fact, here are the two answers, right? Undefined and 0, right? Infinity on the bottom means it's 0, unless you also have infinity on the top. And 0 on the bottom means it's undefined, unless you also have a 0 on the top. That's what's important to remember. Got to match, then it's required. All right, so let's do some L'Hopital examples. I'll just, you know, I'll kind of build one up, see what happens. Let's see if I guessed right that it's a L'Hopital setup. Limit x approaches 0. Oh, sorry, that shouldn't be green ink. We don't know whether it's green, the regular kind, or blue, the L'Hopital's kind. So I won't even say that we're going to do a L'Hopital's. I'll just say let's try the limit as x goes to 0 of, how about cosine of x? Cosine of x um, over x squared. That sounds fun, right? Well, we have rules here, right? I mean, we know that the cosine of x is a continuous polynomial, and we know a continuous curve, and we know x squared is continuous also. Every polynomial is continuous, and sine and cosine are continuous. The other four trig functions aren't. They've got those vertical asymptotes. So when a function is continuous, you can just evaluate, just plug in 0 and see what you get. So the cosine of 0 over 0 squared. Uh-oh, we have division by 0. Is L'Hopital going to happen? Well, what's cosine of 0? Well, you better remember it's 1. So that is a number over 0. Anything divided by 0 gives you undefined. Anything over 0, undefined. What if, however, what if it was sine of x? Over x squared. What if that's what's going on? That's a little more interesting, right? They're still both continuous. It's not a problem. You still get to just go ahead and evaluate sine of 0 and 0 squared. But this time you get, oh, the sine of 0 is 0. So you get 0 over 0. Now you can use L'Hopital. I'll switch to blue, right? I'll just write L apostrophe H, right? L'Hopital applies now that you have one of the two forms, 0 over 0. L'Hopital is very simple. Just redo the limit on the derivatives of the parts of the fraction. What I mean is, you know that derivatives of fractions are kind of annoying. You've got to use the quotient rule, right? Bottom derivative top, top derivative bottom, a subtraction sign, something squared, right? That's a mess. What I mean here is just take the derivative of the top, derivative of sine of x is cosine of x, and then take the derivative of the bottom, derivative of x squared is 2x, and re-evaluate. See what you get when you take this limit. And that's going to be the answer. This is cosine of 0, and this is 2 times 0 is 0. Cosine of 0, oh, that's just like before. Cosine of 0 over 0, that's undefined, right? Now this is different, remember? This is actually undefined. That's the answer. When you have a 0 or a over 0, or an infinity over infinity as a limit, you don't yet know whether there's an answer or not because you have to apply L'Hopital's rule. Those special forms, these are called indeterminate form. Remember how I said you can't figure them out? You cannot determine them. Indeterminate, right? R-M-E-N-T. You can't determine them, like in being opposite. Insoluble, a problem that's not solvable. Insufficient, not having enough. Indeterminate means you cannot determine the answer. It's just stuck at indeterminate until you apply L'Hopital's rule. These green examples down here, again, they're messy, but they're messy in an undefined way, right? That's a specific answer. Basically, it's sort of like off to infinity, or you know how a vertical slope is undefined, but that's because it's a number over zero, right? That's a specific answer, even though the limit itself can't be defined as a number. And these other ones just, the limits became zero, even with the infinities on the bottom. Indeterminate form is what happens, is required to happen before you use L'Hopital's rule, and then you apply it. And sometimes the answer is, wait, blue ink, right? Sometimes the answer is just, oh, that limit is undefined. Let's try another one. Let's try another one, see what happens. How about the limit as x goes to infinity? Wow. Of, well, why don't we just use the top one, the second one again, the sine of x over x squared. We saw it went a little crazy at 0. Let's see if it does the same thing when we take the limit going towards infinity. Well, this is where you have to get a little bit informal. Remember, the sine of x is going up and down and up and down and up and down, but remember, it only has a maximum height of +1 and a minimum height of -1. So, right, it oscillates, right, goes up and down between, right? So this is some number. As x goes up, you keep going up and down between -1 and 1 and hitting all values in between also. So the top is always between -1 and 1, right? The bottom, infinity squared, well, infinity squared is kind of like, right, infinity. The bottom is getting larger and larger and larger. So we always have, right, we always have a small number up here, and then on the bottom we have an ever increasing number. It's continuing to go up, and it goes up without bound. That's really what the symbol infinity is meant here. Well, if you've got a number somewhere between -1 and 1, and you're dividing it by larger and larger and larger numbers, the results are getting smaller and smaller and smaller and smaller. So 0 is the answer. No blue ink. This was not a L'Hopital's problem. We didn't get infinity over infinity or 0 over 0, so we just kept reasoning through, right? Regular limits can be a little mind-boggling, but, right? But you can't use L'Hopital when it's not appropriate. You'll get the wrong answer. How about something like the limit as, let's do another infinite one. As x goes to infinity, let's make this interesting. How about 3, 3x squared? Yeah, 3x squared plus 10. There's a polynomial. And how about the bottom of this is x cubed. Okay, limit as x goes to infinity, right? Well, right, x is going towards infinity, so when you square that larger and larger number, when you square it, multiplied by itself, it gets even larger, even faster. And when you triple it, it gets even larger. And when you add 10, it gets a teeny tiny bit larger, but it's definitely infinity. Same thing with the cube. You take a large number and cube it, it gets larger, right? Yep, definitely L'Hopital. Time to break out the blue ink. Okay, so what we do, the answer is the limit as x approaches infinity. And to apply L'Hopital, we just rewrite the fraction with the derivatives. The derivative of 3x squared plus 10 is 6x. The derivative of 10 is 0, so that's kind of cool. That term drops out. And the derivative of the bottom is 3x squared. And I can do a little canceling now. I have x over x squared. So now I can rewrite this, and 6 over 3 cancels as a 2, right? So I cancel the x out here, and that cancels my square there. I just have 2 over x as the answer. That's just the algebra, right? But then I'm still taking the limit as x goes to infinity, remember? So I get 2 over infinity when I apply the limit. And remember, 2 is a constant. Dividing by infinity, that really means dividing by a larger and larger number, which means you're getting a result that's smaller and smaller and smaller. I've said it before, right? That means the answer is 0. The answer is 0 by L'Hopital. Kind of cool stuff. By the way, they taught you tricks for double polynomials. These are called rational functions. They taught you some tricks in regular limits. That means you didn't have to use L'Hopital to get this answer. But, you know, sometimes those tricks that you were taught only work for polynomials, right? I think the trick was, I'll do this just to briefly remind you, they generally wanted you to divide by the highest degree polynomial on both the top and the bottom. And then just, that cancels out to 1, and then you would analyze each term. 10 over x cubed, well, as x grows large, that goes to 0. 3x squared over x cubed, that does simplify to 3 over x, and 3 over x, and of course x goes to infinity, so that's 3 over infinity, and that's the 0. Just wanted to remind you there are sometimes other methods. However, when it's a non-polynomial over a polynomial, those little polynomial tricks don't work. They're specialized. They did want to give you as much power as possible before you learned L'Hopital. So they gave you a specialized methodology for polynomial over polynomials, rational functions. Let's see. Anything else we want to do? Oh, just for fun, I'll do this one quickly. I just want to change. I'll save a little time. I'm just going to change one thing. I'll keep the 3x squared and I'll keep the 10. And this time I'm just going to make it over just x, right? Same thing here, limit as x goes to infinity. You, of course, get infinity over infinity again. But this time, when you take the derivatives, right, you're still taking the limit. When you take the derivatives, it's 6x, right? Same deal, I haven't changed anything. But the bottom is, the derivative of x is just 1. So that simplifies out to 6x. And remember, I should have switched to blue ink. Sorry, I'm making that my convention, right? Blue ink, right? But remember, this was x goes to infinity. Still x goes to infinity, right? 6 times infinity is infinity, right? So you get undefined as an answer. So you can still get undefined as an answer. Here's another way you can get undefined as an answer when you're applying L'Hopital. Sometimes it gets you an answer. 2 over infinity is read as 0. Yay, I have an answer. Sometimes it just gets you undefined in a different way. Again, you could have used the old polynomial trick or even a table of values, and you would have seen that this thing is growing without bound. Just like if you did the table of values for the top one, you would have seen it is shrinking towards 0. So that's basically it. There is one fourth case, and I will write that one in red. It's the nasty case. I've used polynomials here in most of my examples, but I do want to remind you that we did do a sine example, right? If you had sines and cosines, if you had trig functions, remember how the derivatives, right? Derivative of sine is cosine, derivative of cosine is sine, negative sine. If you have something involving trig divided by trig, and somehow you're getting 0 over 0, for example, or even infinity over infinity, because we know some trig functions have vertical asymptotes, they go off to infinity, you might have to apply L'Hopital. But because sine becomes cosine, cosine becomes sine, sometimes when you apply L'Hopital, you get another undefined, indeterminate, 0 over 0, or infinity over infinity. So you have to apply L'Hopital again, and then you get another indeterminate, right? And what you start noticing is, oh goodness, I came back to the original function. It's pretty rare. There are a couple of examples in the diagnostics and the textbook, but be on the alert that there is a fourth kind of answer. Um, that's the fourth case. It goes in a circle. So no answer because your L'Hopital's rule goes in a circle. We can call it a repeating cycle. I'll call the second and third cases. Those are where you get answers, right? Maybe it's 0 because it turned out to be 2 over infinity, but that's a number. Maybe it's just, 3 over 7, right? You just get an answer. So that's L'Hopital works. I'll put works in blue, right? And here's the first case, right? I'll call it the first case because it's the first thing you check. The first case is L'Hopital does not apply. Maybe I should have made the top three third, second, and first. And the 0th case is L'Hopital does not apply. And there's no blue ink here. Does not apply. What's that mean? L'Hopital's rule demands that you have 0 over 0 or infinity over infinity, simplified form. There are others that you do not have to worry about. You have to have one of these two forms, indeterminate forms, in order to apply L'Hopital. Sometimes you get a number, and sometimes you get undefined, right? You might actually apply L'Hopital, as we did in that final example, and get undefined. It's not that L'Hopital didn't work, it's that L'Hopital worked great and told us this limit is undefined, can't be computed. Or it can, right? That's the second case. The other examples where you do get an answer. The fourth case is it feels like you can apply it, but then you apply it and you get another indeterminate, and you apply it and get another indeterminate, and then you apply it and you realize you're going around in circles because the algebra for the two fractions, probably involving trig, just keeps repeating itself. So again, right, it's sort of worse than undetermined. It kind of stays indeterminate. Nothing can be done with L'Hopital. There might be an answer, but you'll have to get it some other way, calculator or other tricks. And of course, do not forget, L'Hopital does not always apply. When you take a limit and it isn't the perfect partnership of 0 over 0 or infinity over infinity, then you just have to deal with whatever answer you get. Thanks for listening.